So, happy Monday. Today is class number 14. In terms of where we are in the semester, we have 42 meetings altogether, but that includes like test days and quest days and review days. In terms of days when we see new material together, there are exactly 30 of those. And today we are on class number 14 out of 30 days of new material. So we're pretty much at the halfway point. Next class will be our halfway lesson. Today we talk about perhaps the most famous theorem in all of mathematics, the Pythagorean theorem, and then start a major topic about laws of exponents. And you can see that next class it's exponents. Working with radicals has to do with exponents, and then rational exponents. So lots and lots of stuff coming up on exponents. Okay, so there's a brand new packet. Go ahead and grab one that's on the table. This is the last packet that I will hand you this semester. You're also going to grab from the table that chart with all the numbers on it. We'll reference that in a little bit. So you have two handouts today, big packet and then single piece of paper. Okay, so we need someone reading our daily summary here. Page number 1. Lucas, go ahead.
In this lesson, we solve story opportunities with Pythagorean theorem and begin to our exploration exponent certain rules, simplify expressions containing exponents.
Thank you. Number 1, Ramses. Okay, so I think that you guys have all seen that equation before, right? A squared plus b squared equals c squared. One of the biggest mistakes people make is not making sure that the right thing is by itself in this equation. And the right thing is the hypotenuse. How can you tell which one is the hypotenuse?
The longest side.
Yeah, it's the longest side, and it's the one that's far away from the right angle, right? The opposite side to the right angle. Okay, let's go to 2, Jeremy. Okay, so we've got our home entertainment center, and it has this rectangular space for our TV, and it's 17 by 21 inches. And the TV is a 27-inch TV, right? Which is kind of strange if you ever sit down to think about it. A TV is a rectangle usually. Rectangles have a length and a width, but you only get one number, right? You guys don't have two numbers associated with your TV. It's 27 inches, or it's 18 inches, or it's 35 inches, 55 inches, right? What are they measuring? What is it? Is it the length? What do you think they're measuring? Yeah, it's the diagonal. Why are they choosing to give you, out of all the things they could measure on your TV, let's say this is your TV screen, why do they choose to tell you the length of that number? They're going to give you one number. Why did they pick that one? It's the longest thing you could find, right? If you're going to measure anything about this rectangle, the absolute biggest number you can measure is that diagonal. It is pure marketing. It's all that it is. They're going to make this thing sound as big as they possibly can by choosing to tell you only the diagonal. Okay, so let's go ahead and find the length of this diagonal for the 17 by 21 hole that we have here. So we're going to use our Pythagorean theorem. So Pythagorean theorem, it's again a squared plus b squared equals c squared. The 17 and 21, what letters are they? They're A and they're B. So we do 17 squared plus 21 squared equals C squared. And I'll go ahead and label this purple thing as C. How do I know that A and B are 17 and 21? Because what? They are the two measurements given, but how do I know that I shouldn't have said A is the unknown and C is 17? It's true, wouldn't make sense with the numbers given. Looking at that picture, how do I know that C is this thing that has to be by itself in the equation? C is the diagonal, opposite the right angle, right? There's your right angle there. So C is the hypotenuse. It's got to be by itself. Okay, and then here it's just a matter of crunching through the calculations. Okay, so 17 squared, you might not happen to know it, but it's up here somewhere. These are the squares up here. So how much is 17 squared? 289. Plus 21 squared, okay, our chart just runs out. It's 441. And then we smush those things together. Let's see, 0, 483, 730. Somebody check that for me. I think that's right. And then how do we solve this thing for C? We'll take the square root, right? And the square root of 730, you can punch into your calculator. It's just a button. Somebody have this number for us? Savannah? Okay. So 27.02 is the length of the diagonal of the space in your entertainment system. So will it fit or won't it fit? Will it fit or won't fit? That's the length of the space. Yeah, the space is just a hair over. Hey, well, I made the problem up, so that's how we add the excitement to the math class, right? All right, so in theory, it just barely fits. You better hope that there's no that nobody's off with their measurements. All right, number 3, let's go to Christian. Okay, so 7 squared we know is 49, but why? It's because 7 times 7 is 49. How do I know I should have 2 7s there? Because that's what the exponent is, right? Just telling you how many 7s there are supposed to be. 5 to the 4th is really 4 copies of the number 5 all multiplied together. Yes? I remember back in, I don't know what grade you're in when you first learned about exponents. I feel like I was in 6th grade when I took this like quiz on exponents. And for 7 squared, I put 14, and for 5 to the 4th, I put 20, and I said, well, this is silly. Why does a teacher keep putting these things up on top? I know we're just supposed to multiply the two numbers together. So my grade was 0 on that quiz. That was not my best performance in math class. But now I understand it's not just multiply, right? It's repeated multiplication. And 2 to the 8th is 8 copies of the number 2 all multiplied together. Turns out to be 256. An exponential expression is something that looks like x to the n, a number to a number. X is the base, n is the exponent. Definition, there isn't much to be gained from looking at that. It's really just explaining exactly what we did up above. And let me preface these first laws of exponents here by saying that exponents are typically one of the toughest topics for many students in this class, in intermediate algebra. And it's because there are going to be so many different exponents, and sometimes you can apply different rules in different orders and still get the same answer at the end, but other times you have to be really careful about the order in which you apply these properties. So I just want to put out there that I know it's Monday morning and it's the first day back, but you really got to wake your brains up if they're not like on alert at the moment, because this is the beginning of a difficult topic for many algebra students. Okay, so these 5 properties are going to allow us to take exponents and somehow simplify them, clean them up, or rewrite them in a different way. Suppose that we had 3 to the 5th times 3 squared. The question is, can you rewrite that as 3 to some other power? And the answer is yes, because if you write 3 to the 5th out by writing 5 copies of a 3, and then multiply that by 3 squared, 2 more copies, how many 3s do we have? 7? And so everybody buys that 3 to the 5th times 3 squared is really 3 to the 7th. So what's our rule here? What do you do with the exponents when it looks like that? When you put them together by adding them, right? 5 and 2, that's why it's 7. It's because we added them. But I'm just going to put out there right now that another reasonable answer would be 3 to the 10. What did I do to the exponents? If I say 3 to the 10? I multiplied them. And that's a perfectly reasonable thing, especially because there's no addition in this problem. This is a multiplication problem. So this is, again, the beginning of why this is a difficult topic for many, is that we have these properties that, all right, so this property is true, but 3 to the 10th is another reasonable answer, and it is just flat wrong, and it will always be wrong. And so what we're going to have to do is make sure that that we get really comfortable with these properties and also recognize when there are things that seem reasonable that just aren't true, like 3 to the 10th is just never going to be the right answer to this. But the reason that I've got these examples laid out here, as opposed to just saying, hey guys, here's the property, x to the m times x to the n is x to the m plus n, is that I'm trying to ground us in specific calculations so that it will make sense that we need to add those powers up as opposed to multiply them. Okay, next example. 3 to the 5th over 3 squared. If we just list out 5 3's on the top, 2 3's on the bottom, and then cancel. Cancel, 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 cancel. How many 3's are left? 3 of them. What can you do with the original 5 and 2 to recognize there will be 3 left over? Is subtract them. And so this is our property here, is that really you can take the 5 and subtract the 2 and get 3 copies of the 3. Next example, 3 to the 5th squared, 3 to the 5th squared. Okay, there are a couple of things that I could do with the 5 and the 2. I could add them just like before, right? Maybe the answer is, again, 3 to the 7th. I could multiply them, right? 3 to the 10. Heck, I could even do 5 squared, 3 to the 25th. Only one of those things is right. Let's figure it out by looking at the numbers. 3 to the 5th squared is really 3 to the 5th times 3 to the 5th. Agree? That's what it means to square something. And then I'm just going to go ahead and list out 5 3's, followed by 5 more 3's. So how many 3's are there altogether? 10. So it turns out, what are we supposed to do with those powers? Is multiply them. But again, there are other reasonable answers besides multiply, but they're all wrong. And so if you're not sure, don't guess. Just tie it into something you know, specific numbers. Okay, next example. 3 times 4 to the 3rd. 3 times 4 to the 3rd. Okay, sure, the answer is 12 to the 3rd, but that's not what we're after here. 3 times 4 to the 3rd really means 3 copies of 3 times 4, yes? And then if you just imagine shuffling all the 3's to the front and the 4's to the back, how many 3's do we have in the front? 3 of them, there they are. And how many 4's do we have? Also 3 of them. And that's really 3 cubed times 4 cubed, yes? So in some sense, when you have a power on top of a multiplication, that power distributes in. Distribute is not the right word because distribute means something else technically, but that's what it feels like to me anyway, is that I'm taking that power and distributing in to both of those factors inside, right? Okay, and then finally, the same kind of thing happens when you have division raised to a power. The final answer here is just 3 to the 3rd over 4 to the 3rd. You can see everything written out there. Okay, so let's go to the next page. And we'll go to Tyler for 5. Okay, so the first one, -4 squared. Second one, -4 squared. Third one, -4 squared. Again, there are only one right answer to each of these problems, and lots of ways to get them wrong. So the first one, -4 squared. That really means what? What times what? -4 times -4. Everyone agree? And what does that equal to? 16. The answer to this is 16, not -16. But looking at the middle one, a lot of people are going to read that the same exact way. They're going to say, oh, it means -4 times -4. But think about the order of operations. You guys remember PEMDAS? There's no parentheses, but I do see an exponent. And that negative is really like -1 times. You guys agree? The negative is really like -1 times whatever. So which goes first, the multiplication or the exponent? According to PEMDAS. Exponents come before a multiplication, right? So we're supposed to do that exponent first, leave the multiplication until the end. So this is -1 times 4 squared, which is 16. And -1 times 16 is -16. And that's the answer to this one. A lot of students give exponents more reach, more power than they really have. That squared is not strong enough to reach and grab that negative sign. The negative sign is just waiting in the front, waiting for that weak exponent to do its thing. So the answer here is not +16, it's -16. Last one. So here, how much is this piece? We did that first, right? That piece is 16. So what's the answer to this problem? Is -16. Everybody see it? Which means it is not okay to see two negatives next to each other in this fashion and say, oh, they just cancel, right? Negative, negative makes a positive. Because if you just cancel them, what will you get as your answer? You'll get +16, which is not right. So how come you can't say negative, negative makes a positive? Well, you can, but you're not allowed to ignore the order of operations. That exponent needs to come before the first negative has anything to do with this problem. Again, lots of ways to get these guys wrong, and only one right answer. Okay, and then number 6, let's go to Marcy.
In other words, any zero power.
Okay, so this is one of the strangest properties you'll see. It's also one of the easiest to apply. If you have a calculator handy, you can just test it out right now real quick. Any number raised to the 0 power is 1. 9 to the 0, 8 to the 0, -15 to the 0. If you have your calculator, just type it in real quick. Make sure your calculator knows this property. Any number to the 0 is 1. It feels like maybe it should be 0, but it isn't. Any number to the 0 is 1. So first blank here says 4 to the 0. How much is it? 1. The next problem looks intimidating. 5x to the 4 over y to the 17. But the whole thing is raised to the 0, and anything to the 0 is 1. Right? So it's a gift. Doesn't matter how complicated that stuff is. If it's raised to the 0, it's 1. -3r to the 0 is 1. Anything to the 0 is 1. Okay, this last one is the tricky one. The exponent there is only touching what? The r. The exponent has no effect on the -3. So the -3 is sitting there waiting for you to do this piece first. So this is really -3 times what? 1. R to the 0 is 1, but this answer is -3. Again, don't give the exponents more authority than they have. They are very weak. They don't reach far. The only way to make an exponent reach is to put parentheses. Okay, so the activity starts on the next page. Let's see if we can get through all of these different properties of exponents. You'll start with a Pythagorean theorem example.